Okay, so our next speaker is Akimasa, and he will be talking about lambda calculus and parallelism via parallel reductions.
Thank you. My name is Akimasa Morihata from the University of Tokyo. And the topic of my talk is to introduce lambda calculus equipped with algebraic simplification and to demonstrate that lambda calculus is very useful for developing parallel reductions by equational reasoning. So our motivation is to understand and formalize parallel reductions. So parallel reduction widely used for calculating a total number and average and maximum value and something like that, and often regarded as a primitive for parallel computing. But my argument is that parallel reduction is still not understood well, because most of existing systems support only a specific form of parallel reductions and cannot parallelize complex parallel reductions, such as, for example, reduction or summarization concerning more than one operators, such as calculating power series using multiplication and additions, and also summarization using a conditional branch or jumps. And moreover, summarization may cause on tree with some complicated traversals. For such cases, in order to understand how to parallelize these reduction or summarization patterns, we need solid foundation. And in this paper, new lambda calculus is introduced. That name is Lambda AS. Lambda AS is a lambda calculus equipped with algebraic simplification. The idea is that parallel reduction is essentially based on algebraic simplification. That is not my invention, but many papers say that point. But each paper dealing with slightly different situations. Some of them consider loop parallelization, and some of them consider parallelization of list operations such as folders, and some consider tree operations. And in this paper, the objective is to unify these existing approaches by using lambda calculus. So the reason is that lambda calculus have higher order systems, of course, and the higher orderness can encode several computation patterns inside it. So if we extend lambda calculus with algebraic simplification, we should be able to unify these approaches. Actually, in this paper, we show that several parallel reduction patterns can be easily developed. The key weapon is equational reasoning, and of course, we are based on a purely functional setting. Equational reasoning is a perfect item to systematically developing parallel reductions. And also, algebraic simplification may lead to some exponential blow-up of expressions. So in order to avoid such dangerous simplification, we provide some type system to guarantee some kind of smallness of result of simplification. Now let's go into the technical detail. Lambda AS is called by value simply typed lambda calculus with semi-ring operator and special abstraction operation, delta abstraction. In this talk, we only consider addition and multiplication as a semi-ring operator. So the syntax of lambda AS is either variable, function application, lambda abstraction, numeral constant, addition, multiplication, and delta abstraction. So only non-trivial operator is the delta abstraction. In this calculus, lambda abstracted expression is a value, and delta abstracted expression is function, just like a lambda abstracted one, but this is not a value. Its function body is to be simplified before its argument is passed. For example, let us see this expression. So if we have lambda abstracted expression, then evaluation of its body is postponed until its actual argument is passed. But here we have delta abstraction. So its body is immediately simplified by using the algebraic property of addition and multiplications and obtain value that is a lambda abstracted term. We use this delta abstraction for providing the possibility of parallel evaluation. For example, consider this expression. Here, argument can be evaluated, and if the function is abstracted by lambda, then function cannot be evaluated anymore, so we cannot obtain parallel evaluation. But here we have delta abstraction. So we can simultaneously evaluate function part and argument part. Later we will see this is the key to formalizing parallel reductions. Unless delta abstraction is concerned, the evaluation is very usual. So for example, this kind of expression, we can see that function and arguments are value, and so we just apply usual beta reduction to replace f by argument, and then we encounter delta abstraction and argument, so we do parallel evaluation. And the function part is simplified by somewhat complicated computation and obtain this kind of formula. Now let us see how to formalize parallel reduction by using a delta operator. So first example is very simple, summation by loops. So for each element, we add the element to the accumulation parameter. Okay? So in order to parallelize this summation function, what we would like to have is a divide and conquer implementation. So we have assume that we have a left sublist and right sublist, and if we can process these both sublists in parallel, then we can obtain divide and conquer implementation. A possible expression is like this. So left sublist can be evaluated as usual, but since right sublist requires the result of left sublist, the right sublist part should be a function. But of course, this is not parallel, because this lambda abstraction blocks the computation of right sublist. This is a difficulty of formalizing parallel reduction in a standard lambda calculus. But in our calculus, we have a delta abstraction. So instead of using lambda abstraction, we insert delta abstraction here. Then we can do parallel computation, as we can see. So given a list, say 531762, we divide the list into two parts, and the left sublists are calculated as usual, and the right sublists are simplified by using the algebraic property of plus and obtain function. And then you can see that essentially for right sublist, we are computing a summation. So this can formalize the parallel reduction over summations. This approach can be used for dealing with more complex cases. For example, consider this special summation that breaks if it encounters negative values. You can see this function is more difficult to parallelize because this depends on the order of element. But actually, in our framework, we can do the same thing. So let us derive the divide and conquer implementation for that. So for processing right sublists, we can use the same trick as the previous. So it waiting for the result of left sublist, but use delta abstraction. In order to formalize left sublist, we should be some careful implementation, because computation of left sublist may cancel the computation of right sublist because of the break. But we all know that such breaking can be expressed by using a continuation. So computation of left sublist take the continuation and discards the continuation if break occurs. Maybe this is somewhat complicated, but important point is that this is just a sequential programming. We all know this thing. We all know how to prove correctness of this program based on equational reasoning. The only thing in this program interesting is the delta abstraction. That is only concerning a parallelism. Now we obtain parallel evaluation. So, for example, given a list 5, 3, minus 1, 7, minus 6, 2, or thing, and divide it to 2 parts, and simultaneously evaluate both parts. Right sublist is simplified by using associativity of plus, and left sublist is evaluated as usual. Interestingly, this example expresses the speculative evaluation pattern. Now we have seen that algebraic simplification is very useful for formalizing parallel reductions, but there is a problem. Simplification is not as easy as we expect. So there exists several approaches for simplification, for example, factorization or expansion, and wrong approach may lead to exponentially large expressions. That is not a simplification and useless for parallel evaluation. In order to remedy this problem, we require that simplification must result in linear polynomial. And this restriction is used by several studies to formalize practical parallel reductions. And so I expect that this restriction is somewhat reasonable. And under this restriction, for example, delta x, delta y, y times x is stuck term because this consists of the multiplication of delta abstracted variables. And in addition, under this restriction, only base type variable can be delta abstracted because for function types, it is not easy to provide a good strategy for simplification. And in order to check this requirement, in this paper, type system to guarantee safety is given. Here we formalize the property of lambda AS. So first theorem 3.1, says that lambda abstracted term and delta abstracted term are observationally equivalent if both successfully evaluated. Of course, this is not always occur because delta abstracted term can get stuck because of the violation of linearity. But the following two theorems guarantee the standard of preservation and the progress property, arguing that typeable term cannot get stuck. So by combining the type system and the delta abstraction, we can say that delta abstracted term is observationally equivalent to lambda abstracted term. So it is safe to replace lambda to delta unless type system rejects it. The paper contains more discussions, and of course, the paper contains a formal definition of reduction semantics and type system, and of course also contains a proof of these theorems. And in addition, the paper contains the development of more non-trivial parallel reductions, including the prefix scan, prefix sum, and tree reduction, and even summarization based on tree accumulations. And also, the paper discussed some extension of this lambda calculus, including dealing with non-commutative semirings and introducing fixed point operators. Moreover, the paper contains some encoding of the type system of lambda AS by standard Hindley-Milner typing system that may open a possibility of implementing this lambda calculus inside the standard programming languages such as Haskell or OCaml. So if you are interested in these topics, please read the paper or ask me. Let me conclude my talk. So in this talk, I introduce lambda AS, lambda calculus with algebraic simplification. So this is, I would say, modest extension of standard lambda calculus, and it only possibility of simplification of function body based on algebraic properties. But this extension is very useful for formalizing or developing parallel reductions. And also, in order to support the development of efficient parallel reductions, we provided a type system that excludes somewhat useless case of simplifications. But of course, that is not the end of our travel. So original motivation is, of course, to provide powerful automatic parallelization method, but this calculus does not provide such things. So in order to provide efficient or powerful parallelization method, we should have some strategy of introducing delta abstractions. But here, currently, I have no idea about that. And in order to provide a good strategy, possibly inference of parallel evaluation cost is very useful. And also, if we would like to write efficient parallel program based on this calculus, compilation to existing language is hoped. Thank you very much.
We have a question from Slido. Okay. How does Lambda AS compare with something like pi calculus?
Oh, I haven't considered pi calculus at all. Yes.
We have a question from the floor. We have one in the back there.
Do you know about the relationship between the delta and lambda abstraction and the kind of things you can do in call by push value? As in, can you interpret this calculus in call by push value, or do you know?
Sorry?
There's a calculus called call by push value.
I haven't aware of call by push value calculus.
Okay, all right, thanks.
Another question from Slido. Could delta be seen as a let rather than lambda?
Yes, that is a good question. And actually, for encoding this type system to Hindley-Milner type system, we use a let polymorphism because in this calculus, delta has two some role. First, to pass some unknown value to the body, and second, it as interpret as lambda. So this situation can be captured by let polymorphism. So in this sense, delta is very related to let. Yes.
I think we had a question in the corner. Can we get him a microphone?
So why do you need a semi-ring as opposed to a semi-RNG without the identity?
Sorry?
Why do you need a semi-ring? Why do you use a semi-ring as opposed to a semi-ring without identity or a even more bare bones algebraic structure?
Okay. So one reason is that semi-ring is very easy to provide a good strategy for simplification, especially when we require linearity of polynomials. Of course, other algebraic structure can be used if we can provide a good strategy for simplifying bodies, and in addition, we can provide a good type system to guarantee successful simplification.
Then we have a question from Slido. How do you avoid simplifying expressions that are so small that you do not overset the overhead of parallel synchronization?
Okay. In this paper, constant overhead for parallelization is not so simply ignored. So delta abstraction may be simply useless. In such a situation, no solution is given in this paper.
Question from the floor.
So why did you pick doing simplification based on equational reasoning rather than doing some form of partial evaluation? Like you could evaluate partially and just stop the evaluation when you can't go forward anymore.
Okay, so this is a FAQ. So actually, this simplification is very related to partial evaluation, and especially online partial evaluation. And I would like to say that it is just a partial evaluation, but of course there exist some subtle differences. And so what I can say is that the first thing is this. So some relationship between partial evaluation and parallel reaction has been already pointed out, especially by database people, to provide distributed evaluation of queries. And in that sense, this paper can be seen as a generalization of these results to general purpose programming languages. But currently, I'm not really clear about the connection between partial evaluation and this calculus, and so I would like to study more about that direction.
A question from Slido about generalizing your simplification.
Mm-hmm.
You do it for algebraic expressions, numeric expressions, but if you wanted to generalize it to other sorts of systems, what are the constraints that you would have to make this work?
Yes, so yes, simplification is somewhat pluggable part of this calculus, so any other structure can be used if, as I said, good strategy for simplification is provided, and the goodness can be somewhat estimated by type system. So, but as far as I know, most existing practical, so parallel summarization simply use this kind of algebraic structure. And some exception is the previously I mentioned, the one that database people use, that somewhat use data structure similar to so Boolean expression to express the process of summarization. So in order to deal with such situations, maybe more extension to the calculus is necessary.
And maybe one more question from the floor.
Do you have in mind an efficient compilation scheme to machine code for this sort of calculus?
I would like to have, but currently no.
Okay, thanks.
Thank you. Let's thank the speaker.
Thank you very much.